Lesson 9.5 variation. So your book is going to look at what they're categorizing these four categories of variation. There's direct, like y equals kx. Let's get down here to inverse, like y equals k over x. Right? And then joint and combined, which could be some combination of those. Here, show you guys a graphical version of the main two, which are direct and inverse. Right? So here in red could be like y equals 2x. Right? So that's it's basically just a linear relationship that goes through the origin, right? You call it direct. So if you double the x value, you're going to double the y value, or if you triple the x value, you're going to triple the y value, right? If you multiply x by a factor of 5, then y also gets multiplied by a factor of 5. That's all direct. That's all that red curve, right? Well, what about this blue curve, this inverse relationship? I've got an example, y equals 2 over x. Well, now as x is getting bigger, y is getting smaller, or vice versa. If x gets smaller, y gets bigger. Okay, so it's like an upside down type relationship. All right, so all right, and then again, a joint could be something like what if you throw more variables in the mix, right? Like we have x, y, and z, right? Okay, so y could be directly proportional to x, but also directly proportional to z. Okay, so now you've got more variables that you could change. And then something combined is similar idea, but there might be an inverse relationship also thrown in the mix, like y and z here. Okay, notice all these I tag on some value k. Now your book does not always do that, but I like putting the k there to represent maybe like the slope of this line or how steep is this line, something like that. I might do that. I think that actually makes some of these easier to think about and solve. So let's jump into first the book examples and then some of the questions later on. Example one. Example one. So we start with direct. Y varies directly with x. When y is -3, x is 24, find y when x is -16. So as soon as I see direct relationship, I'm already thinking in terms of y equals kx. Okay. Now your book just hops straight to the proportion, but I'm gonna throw in this middle stuff that includes this k, which is like the slope of a straight line, because again, I think it makes this easier to think about. They said when y is -3, x is 24. Okay? So if I plug in 24 for x, I'll get -3 for y. Okay? Well, that allows me to solve for k. I could just divide both sides by 24, right? Over 24, over 24. It looks like k is going to be -1/8. Okay. So now to make an exact equation, I could say y equals -1/8 times x. Okay. And if you want to check your work, plug in 24 for x. 24 divided by -8 is -3. Bing! It works out. Okay. But what we're really supposed to find is what is y when x is -16. So I could say y equals, okay, well, I know what k is. It's -1/8. Okay. And for x now, they want that to be -16. That's -16. That's the same thing as -16 over 1. 16 over 8 is 2. The negatives cancel. So y would have to be 2. And that has to be the answer. Okay. So that's what we'd be looking for. Uh, Now, the way your book went about it a little bit different is they skipped through all this case that they didn't even write k or slope or anything like that. Instead, they say, well, a direct relationship, actually, I think I got space right here on the right side of this paper. Let's go ahead and dip in my paper. Okay. As they say, if you have a direct relationship, you could rearrange this as y over x is equal to k. And since that k is the same, regardless of the specific set of y and x values, then this could be equal to some y2 over some x2. Okay, this is y1 and x1. Okay. And then here to run the same numbers, when x was 24, y was -3. Okay. And that's equal to k equal to, and then we're solving for y2 when x is -16. I'll show you guys, well, it gets the same answer. It's just a little bit different way to go about it. All right, so I can cross multiply the -16 and have -3 over 24 times -16, and that should be the answer. Okay, but what does this reduce to? Well, -3 times -16, that's +48. So divided by 24 equals y2, and 24, the 48 divided by 24, that is 2, right? Which is the same thing I got with this other method of including the constant k throughout, right? And so the left half of the paper is the way I would tend to think about it or set this up in my physics class. The right half of the paper is a lot closer to your book's explanation if you're going through reading the book and going through their explanation. But either way, you get the same answer. Okay. All right, how about all right, right, example two, they're calling joint variation. So I think it's going to be really similar to this. We're just throwing in yet another variable. Maybe instead of just x and y, now have x, y, and z. Yeah, there it is. We got x and y and z. Okay. It says y varies jointly as x and z. So example two. So I might say y is equal to k times x times z. Okay. So y is directly related to x, but y is also directly related to z. Hence joint. Okay. Uh, Find y when x is 4, z is -3 if, right? Actually, let's start with everything after if right here. So if y equals -15, put a -15 there, right? And what I'm going to do is I'm going to solve for this k. Once I get this k value, it'll be universal to this particular question. When x is -6 and z is 1, like that. All right, well, yeah, we can get k. Divide both sides by -6, the negatives cancel. Now 15 I know is 3 times 5. 6 I know is 3 times 2, and I divide that over, and the negatives cancel. So it looks like k is 5 over 2. So we can come up with this equation and say y is equal to 5 over 2, and then times x times z. Okay. Now we got this more explicit type of equation. Let's go and find what we're supposed to find. It says find y. Okay, well, this is already set up to find y, so that's nice. When x is 4, put in 4 for x, and z is -3. Okay. Again, x and z, you can think about these being in the numerator. So like over 1 over 1, if that helps. I know 4 divided by 2 itself is 2. And then it's -15. I think it's -30, isn't it? -30. That should be the answer right there. Point. Okay. Okay. Again, your book set up more proportion and skip through ever solving for this k at all. A little bit different way to think about it. If you like the book's method, you can go for that if you like. I would probably recommend this way. That I'm doing it. So example three. Ooh, inverse variation. So m varies inversely with n. So we could say m is proportional to 1 over n, or m is equal to k divided by n. Okay. Okay. N is -4 when n is 6. Okay. So n is -4 when n is 6. That means that this k value right here, cross multiplied 6, is -24. Okay, so that's nice. Now I can make an explicit equation. I can say, well, n is equal to -24 divided by n. Okay. Yeah, if you plug in 6 for n, you'll get -4 for m. That all checks out. We know all that so far. Now, find m when n is -10. Yeah, that's it. So m equals -24 over -10. That would be 2.4. Boom, done. Got it. Not bad. Example four, combine variation. So now maybe we'll get a mix of both direct and inverse. Suppose that A varies directly as B. Example four. So A is equal to, okay, well, let me say about fraction because I know there's probably a fraction coming. I'm going to throw in some constant K that I can solve for. We'll come back to that. I know I'll put B in the numerator because that right there is a direct relationship. That's the first thing you said, direct relationship. A varies inversely as C, so I'll put C down here. If C is getting bigger, A is getting smaller. That looks like an inverse type relationship. Right? It's kind of like the last example we just did, example 3. Some kind of inverse formula. Okay. All right, I think that's all the variables. Okay, find B when A is 6 and C is 28. Okay, well, we can't do that yet, but everything after if is really going to help us out. If B is 7 when A is -49 and C is 3. Yeah, so that very last statement right there, I'm going to plug those values in. When A is -49, so that takes the place of A. Okay. And see, B is 7, so that takes the place of B. C is 3, takes place of C. Okay. So like, by setting it up this way, I can solve for this constant K, and then I'll have an explicit equation, and then I can solve anything I want. Okay. So let's take that -49. I'm going to multiply this 3 and divide it down to 7. Okay. That will tell me what K is. Now I know 49 over 7 is 7. times -3 is -21. So K is -21. Okay. So now that I got that, I know that A is always equal to -21 B over C. Okay. So I'm gonna play out this formula. Right, and now we can go answer their question. They said, find B. So I guess we're solving for this up here. When A is 6 and C is 28. A is 6. All right, we're solving for B. C is 28. You like that? That right? Okay, so got this set up. Now 21, 28 is here, both multiples of 7. So maybe I'll pull a 7 out. Here, let's get some more paper. Continue this down here. Yeah. So 6 is equal to negative. Okay, I pull out 7 over 7. I got a 3 over 4, and I got a B up here. See, the 21 became 7 times 3, and the 28 became 7 times 4. Okay. So B is equal to, okay, take the 6, multiply it by 4, divide by -3. Oh, and then 6 over -3, that's -2 times 4. I think B is 8. And there you go. All right, I got your answer. Okay. Now, this has all been kind of abstract math so far, and fractions and numbers. Okay. But hey, look, here we go. We got a fun word puzzle. Ooh, with bicycles. Bicycles. Let's check this out. Okay, so a rider's speed in miles per hour varies jointly. Ooh, so it's going to be one of these more complex type questions. With the revolution per minute of the pedals and the number of teeth on the front gear, and inversely with the number of teeth on the rear gear. Okay, let's definitely get a picture going on this one. Example 5. All right, let's get a bicycle going. See, got some handles. Let's see, what's this bicycle look like? I think something roughly like this, right? Got a wheel, another wheel, a little seat, right? Right. There's bike, right? Got some pedals here with a gear, right? Now I'm going to put a big gear here, and I'm going to draw a bunch of teeth, right? Because that's relevant to the question. Okay, and then there's this back gear, which has probably fewer teeth, right? I got this bike chain that's going around like this. Okay. Now, look how it's going to play out. Notice I drew the front gear is larger than the back gear, okay? Because if it had like twice the diameter and therefore twice the circumference, let's say, right, then if this front gear makes one complete revolution, this chain moves so far and moves the same distance on this gear as this gear, a linear distance, which means that this back gear would actually make 2 revolutions. Ooh. Okay, so 1 revolution here would be 2 revolutions here. Now that's if the diameter ratio or the circumference ratio was 2 to 1. Same thing, right? I don't know that's same thing here, but just get the idea. Okay, so here we got this pedal, right? We're pedaling this bike. Okay. All right, so a rider's speed. All right, so I'll go ahead and spell out the word speed. In physics, a lot of times I'll use the character v for velocity, but I'll spell it out here. Speed. It says varies jointly with. Okay, so let's get a fraction going. The revolutions per minute. Okay, you know what? In physics, okay, revolutions per minute is more like a unit. What I would call this is angular velocity. So here, I'll just go ahead and point this out. I'll probably just change the speed to v for speed. Okay, and this omega is going to be angular velocity. Okay. That's like how fast is it rotating, and that could be in revolutions per minute. Well, we'll just let that be in RPM. The number of teeth on the front gear, I'll call this, how about F is number of teeth on the front gear, and B is number of teeth on the back gear. Does that make sense? How about N sub F and N sub B? Let's do that. Right. Right. So number of teeth on the front gear, and inversely with the number of teeth on the back gear. There we go. Right. And I'll also throw in some constant so I can come up with an exact equation. Right. And then I can go through and solve this. Okay. Now, before we get plugging and chugging, let's see, does this make sense from a forest for the trees relationship point of view? Okay. Like if you're pedaling faster, Okay. That means you're directly increasing this omega right here, which is the angular velocity of revolutions per minute. Okay. Is that going to make the bike go faster? Yeah. In fact, if you pedal twice as fast, the bike's going to go twice as fast in a linear sense. That makes sense. Okay. Now, what about this number of teeth? Okay, that's kind of what I was looking at before. I was saying like if you have twice the number of teeth here than you have here. I was talking about diameter and circumference, but it could translate to number of teeth, right? They're like spaced similarly, right? Then every time you pedal this front gear once, maybe the back gear moves like more than maybe like twice if it's a 2-to-1 ratio. But whatever the ratio, the number of teeth is, yeah. So I see this ratio shown up here. Yeah, if you want to make an exact equation that fits all these units together and if the speed could be, are they going miles per hour? Yeah, they're going miles per hour for the speed, and that has to correspond to revolutions per minute. How do you do that? Well, this K is going to connect everything together, so some constant. Right, so let's do it. We'll start with, right, we got our model equation. They give us a complete example of numbers that go together, which will allow us to solve for the K. Once we get the K, we'll have a master equation. We can solve anything related to this bicycle. Then we'll go solve the specific question we're supposed to solve. So on a flat stretch of road, rider's traveling 17.1 miles per hour. Uh, Front gear has 50 teeth and the back gear has 16 teeth. He's pedaling at 70 RPM. Yeah, that is a complete set of numbers right there, except of course for the K that we're using those numbers to solve for. So let's call it 17.1. This is miles per hour equals, okay, we're gonna find out what this K is. Okay, we're looking at 70 revolutions per minute. The number of teeth on the front is 50. The number of teeth on the back is 16. Okay, like that. Now we can solve for K. Okay, so K equals, well, it's whatever 17.1 times 16 over 50 and 70 is. Okay, this got weird units. They got miles per hour, revolutions per minute. Okay, so we're going to get really weird units from a physics sense that are going to pertain to like this exact like set of units, right? So the angular velocity is always going to be revolutions per minute and so on. So we've got 17.1 times 16 divided by, and then in parentheses, we got 50 and 70. Right, this is looking like K is equal to, that's a tiny decimal. I wonder what the fraction version is. I'm gonna here show you guys two different ways to do this. You could call this 0.07817 and then miles per hour revolution per minute. Okay. Or if I take reciprocal, this is 1 over 12.79. And then again, miles per hour revolution per minute, these weird units. Okay. So you could have either value of K, it'd be this value in the numerator, or this value in the denominator, right? So either way. Right, so gonna rewrite the speed equation now that we know this K value. Okay, so I'll say speed V, velocity speed, equals, okay. Now, since K could be 1 over the 12.79, I'll just go ahead and put the 12.79 down here. Again, so this RPM over, what's it? No, sorry, NPH, RPM, something like that. Right, I got that. I got number of teeth on the back here. I got number of teeth on the front here. I got the angular velocity in radians, or revolutions per minute, rather, right there. Okay, so I can use this as my model. Here's my model. All right, so now is the actual target question. Find the speed of the rider. So we're solving for this V speed, V velocity. Biking uphill using a front gear with 34 teeth and a rear gear with 23 teeth. Okay, so now it's closer to a 1-1 ratio than before. That's interesting. Maybe should like shifted the gears on while pedaling at okay, also 70 RPM, same as before. All right, so how fast are you going to be going? So where the omega goes, I'm going to put 70 RPM, 70 revolutions per minute. The front teeth is 34. The back teeth is 23. Okay, and this K value, which I moved down here, you call 12.79 in the denominator. Okay, this is miles, no, Hold on a minute. Miles per hour. Did I get this backwards? I'm just looking at the unit over RPM. Yeah. Whoops. Okay, let me fix this. This is miles per hour here. This is RPM here. So this would be RPM and then miles per hour. Okay. So RPM over miles per hour. Okay. I think I got my units back straight. Because the RPM cancels and the miles per hour is in the denominator of a denominator, so it's going to come back up on top, which tells me that the speed is going to be so many miles per hour, which is what I'm looking for. Okay. Let's get 70 times 34 over, then parentheses, 12.79 and 23. Okay, I'm looking at 8.09 miles per hour. There you go. 8 miles per hour. Okay. All right. Let's jump into the main book questions. Okay. So the first few I highlighted are just abstract math, right? And then later on I highlighted some word puzzles. So see some of each. Okay, number 5. Y varies directly as x. So I could say y equals kx, or y over x is equal to k, if you like. Uh, when, okay, y is 35 when x is 7. So y is 35 when x is 7. Okay, that means I can solve for k. Divide both sides by 7. I think k is equal to 5. Okay. Okay, now that I know that, I can go back and say y is always equal to 5x. Okay, direct relationship. Okay, if you graph that, here, mark up the graph real fast. X-axis, y-axis, it would look like this, with a slope of 5 over 1. Quick graph right there. That's it. Now we're supposed to find y when x is 11. 55. Boink. Next one. Number 11. Y varies jointly as x and z. So I think that would be y equals k x z. Okay. Y is 18. Let's plug in 18 right here. When x is 2 and z is 3. 2, 3. Okay. Okay, well, 2 times 3 is 6. If you divide that over, I'm getting a k value of 3. Okay. So in general, now y is always equal to 3 times x, z. Okay. All right, so now we have this equation we'll work with. Right? And what are we supposed to find? Find y when x is 5 and z is 6. Yeah. X is 5, z is 6. Okay. Well, 5 times 6 is 30, times 3 is 90. Boom. Another one down. 17. Y varies inversely as x. So y is equal to k over x. I could think of it that way. Y equals 2 when x equals 2. Okay, so y equals 2 when x equals 2. Solve for k. Then k has to equal 4. So I can say y is always equal to 4 over x. Okay, so now I got this expression. Right, and where do we find here? Find y when x is 1. 4 over 1. Y is equal to 4. There it is. It's a little thing. Boink. 19. A varies directly as B. A varies inversely as C. Okay, so A equals, okay, so some constant times B divided by C. Okay. So A and B have a direct relationship, A and C have an inverse relationship. Find B when A is 5 and C is -4. Okay, well, we can't do that yet, but this last part will let us do that. If B is 12 when C is 3 and A is 8. Okay, so B equals 12 when C equals 3 and A equals 8. Okay, so there's your setup to solve for K. Now I know 12 over 3 is 4, so 8 equals 4k. Divide both sides by 4, k is 2. Now we got k is 2. So in general, I have this is sort of like master equation. A equals where the k was before, I'll just put 2 because k is 2. And then b over c. Okay. So I'm using this right here, right there. That's it. Now we can go answer the question. Find b when a is 5 and c is -4. A is 5, c is -4. Is that right? Yeah. Yeah. And we're solving for that b right there. Okay, so cross multiply the -4. That's -20. Divide down the 2. That'll leave you with b. So I think that reduces to -10. Point. That's it. Whole thing. Okay. Let's try some of these word puzzles. We got, yeah, okay, so highlighted a few of these word puzzles here. Electricity, 23. The resistance of a piece of wire varies directly with its length and inversely with its cross-sectional area. Yeah, this is one that I teach in physics, so give you guys a picture here. Maybe have this wire, right? I'll call it wire. Okay. And it has some length. That's like this L right here. Okay. And some cross-sectional area. I'll call A. Okay, so L for length, capital A for cross-sectional area. Okay. And the resistance, say if we're going from end to end. Okay. Now, could you imagine if this wire was like 3 miles long? It would definitely have some resistance from end to end, wouldn't it? Right? Some measurable resistance. Okay. What if it was 6 miles long, or 9 miles long, or 12 miles long? When you make it longer, 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 that resistance is increasing. Okay, and that's what they're trying to express right here. They say R for resistance is varies directly with length, so L on the numerator, but also inverse to its cross-sectional area. Now, I would normally just put a K here. That's what I've been doing all lesson that I've been recording this. I'm going to put a special kind of constant called resistivity. I'm going to use the Greek letter rho because that's really what this is. It's a material property of this wire. I think they say copper wire. Yeah, they're talking about copper wire all over the place. Copper wire, copper wire. Notice we're sticking with the same material. If they change materials, then this rho would be different. This rho is called the resistivity. It's the resistivity of copper. Okay. So they gave us some values here. A piece of copper, 3 meters long. Oh, 2 millimeters diameter. Now that's interesting. Why did they give us diameter? That's not cross-sectional area. Hmm. All right. Well, here, you gotta put a little thought cloud over here. Because, guys, what's the cross-sectional area in terms of diameter? Because now there's bit diameter on us all over the place. Well, it's pi over 4 times diameter squared. Okay. And no, the pi over 4 bit's gonna end up canceling by the end. So if you didn't know that or forgot that or accidentally put pi or whatever, right? It wouldn't actually affect the answer then. But it is really important to square the diameter. Right? That's a proportion that you definitely need to get this correct. So here, I'm gonna plug that into this, right? Come up with a new expression. So we got resistivity times length over, I'll do pi over 4 times diameter squared down here. That's what we'll be doing. All right. So now we can go plug these in. 3 meters long. So where the L goes, I'll put 3 meters. 2 millimeters in diameter. Okay. Okay. You know what? Since I teach physics, I'm really tempted to just put that in meters. I'm just going to go ahead and do that. So milli, guys, what is milli? It's 1 over 1,000. So when I say 2 millimeters, so it's like 0.002 meters. Okay. Again, even if you missed that, the fact that later on they also bring up diameter in millimeters, that conversion would end up canceling out. Okay. But it is important. You have to square this to get this correct. Okay. Pi over 4 to tell me something about a circular cross-sectional area. And I got this Greek letter rho to represent resistivity. And they must have told us the resistance. Here it is. Here it is. The resistance is 0.0107 ohms. Ohms of resistance. There you go. Okay. At this point, we have enough information. We can find the resistivity of copper. That's what this is. Now, you see what we're going to do. We're going to take this resistance, cross multiply the pi over 4, the diameter squared, and divide by the length. Okay. I'll just go ahead and do that all on my calculator and come up with the resistivity of copper right here. And then later on, we'll be able to solve a target question with a different copper wire. So take the 0.0107 ohms of resistance. I'm going to cross multiply this pi over 4 right here. I'm going to cross multiply this 0.002 squared. I'm going to divide by 3. Okay, hey, okay, that's a tiny, tiny number. See, 1, 2, 3, 4, 5, 6, 7, 8. What do we do times 10 to the 8? Yeah, about 1.12. Okay, and if I was restoring a decimal place, I would say 10 to the negative 8. The unit ends up being ohm meters. I think if you follow through, got ohms, meters, yeah, like that. Okay, so now we know this material property, this resistivity of copper, okay, we're just going to tie back to these relationships. Right, so here's the actual question. And find the resistance of a second piece of copper wire 2 meters long and 6 millimeters in diameter. So we got this. So resistance is resistivity times length over pi on 4d squared. Okay. All right, so I just found this resistivity that goes right here. 1.12 times 10, whoops, 10 to the negative 8. That's ohm meters. Did it tell us the length of this wire? Yeah, it said 2 meters long. So where the L goes for length of it, sorry, 2 meters. Oops, meters. We're dividing by, okay, got a pi over 4 down here. And then diameter squared, 6 millimeters diameter. I'll call that 0.006 meters. And then don't forget to square that, really important detail. All right. Oh, it gave a little hint at the end here. It said the cross-sectional area is pi r squared. You guys know that radius is half of diameter. I just went straight from diameter to area with a pi over 4. Okay, there's different ways to get there. Okay, again, it's really important that you square the diameter. Right, have to get that. Right, a lot of this other stuff ends up. Okay, anyway, let's just go ahead and run the numbers and figure this out. So I'll take. Okay, so I got this answer from before. I'll say times 10 to the negative 8. Okay, so now we're back to that. Times 2 over, and then I got a pi on 4 and a 0.006 squared. I'm looking at 0 to 0.00079. That would be ohms. Let's see, would that be about right? Well, their last resistance was pretty small. Yeah, and this wire is even shorter and has a greater cross-sectional area, so this resistance would be even less than the other resistance they gave us. So this definitely looks reasonable. Yeah, so there you go. A tiny number of ohms. Okay. Take my physics class. Well, I don't have one within reach right now, but we have these multimeters where you can measure current and voltage, and then divide voltage by current to also solve for resistance in a wire. Yeah. All right, so next one, 25. Pressure. The volume of the gas varies directly with its temperature and inversely to its pressure. What they're getting at here is something called the ideal gas law. Again, I had to pick this one because it's a physics type example. If you have a little shiny balloon right here, then the pressure of the balloon and volume of the balloon equals number of moles of gas times ideal gas constant times the absolute temperature. Okay, so we got here pressure, volume. Right. I'll say in this number of moles of gas. Right, so basically how much gas is inside, right? Like if you counted all the molecules. R is some constant, right, depending on what units you're working with. And T is absolute temperature. Right. Again, I know this from teaching my physics class, but how would you know that from what they told you? Well, they literally said this. So the volume of the gas varies directly with its temperature. So, yep, between V and T, I definitely see a direct relationship. And also inversely with its pressure. Well, notice this. Guys, if I took this P and I divided down, wouldn't V be proportional to 1 over P? Right? Or you could cross multiply the P back and put it back how I wrote it here. If you ever multiply two variables together, then that's another indicator, and they're on the same side of the equation, like that. That's another indication that this P and V in this case have an inverse relationship with each other. So P and V are inverse, right? Whether it's they're multiplied together or you divide 1 over, so it's V is proportional to 1 over P. It's two different ways to say they'd be inverse. Okay. Okay. again, if you didn't know this full ideal gas law equation, here, I'll spell this out. Ideal gas law. Then this N and this R could collectively be combined to represent some constant for some specific scenario, right? And you could still solve this question. Okay. Right, here, take a look at this too. Like, since I got a picture of a balloon here, like what if you squeeze on the sides of the balloon, right? You decreased its volume. Wouldn't the pressure inside also be increasing? Like there's a fly flying around. Yeah, I see some inverse relationship there. Right? Or what if this? What if you heat up the balloon? Like I bring a candle up to it and start heating it up, right? So increase the temperature. Shouldn't the balloon probably expand? Right? So it shows some kind of direct relationship probably between the T and the V. Yeah. Right, different ways to think about that. Okay, a certain gas has volume of 15 liters, temperature 290 Kelvin. Notice they gave that temperature in what's called an absolute scale, which is Kelvin, and a pressure of 1 atmosphere. Okay, so we're going 1 atmosphere pressure. We're going 15 liters volume. Okay, whatever the N and the R are, I'll just call some constant. And absolute temperature this corresponds to is 290, and that's Kelvin. Okay. Uh, right. So let's do this. Let's solve for the NR, just whatever that is multiplied together. Again, it's some constant, some constant. Okay. It's whatever 15 over 290 is, which is, yeah, it's like, I think it's like 3 over 58. Is that the same thing? Yeah, make sure. D8, D8 on 3 times 290. Oops. D8 on 3. 15. Yeah, okay, something like that. Okay, so we got that. All right, now the compressed gas volume of 12 liters. Right, so where the volume goes, I'm going to put 12. Okay, all right. Looks like we're solving for P. That's the question. What would the pressure be? Okay, is equal to, well, N times R collectively is like this 3 over 58 number with a bunch of weird units. I'll just drop those. Okay, and then we're going to heat this to 310 Kelvin. 310. All right. Well, the pressure is going to come out to atmospheres because that was the pressure before, and it's embedded in all these constant values. So all I have to do is take this and divide by 12. So this will tell me the pressure in atmospheres. Okay. By the way, do you guys notice that the volume is a little bit smaller and the temperature is also a little bit bigger? Now, for both those reasons, right, if you squeeze on the sides of the balloons to make the volume smaller and also you heat it up at the same time, both of those would cause the pressure to increase. Now, and if the pressure before was only 1 atmosphere, this pressure has to be more than 1 atmosphere. Let's see if that's true. 310 times 3 over 58 times 12. 310. Wait, what's that? It's 3 over 58. It's 12. That's a really big pressure. Is that right? 3 over 58. 290. It's 15. 3 over 58 times 310. Oh, whoops, I did divided by 12. Okay, there you go. Okay, knew something was off. Here we go. 1.34 atmospheres. That looks about right. Yeah. 1.34 atmospheres. There you go. So take 3 over 58 times 310 over 12. Yeah, there you go. All right. That looks reasonable. Go with that. All right, number 61, rent. An apartment costs $N per month. N students share the rent equally. How much would each student have to pay? Okay. So I'll say key is payment per person. All right. Well, let's just take the total rent. They're doing $M per month. So this is rent per month. And we're going to divide it by N. That's students sharing the apartment. Right. Well, okay, we're collectively renting the apartment, right? Okay. All right, so we got this up here. That's probably what they're looking for part A is something like that. How does the cost per student vary with the number of students? Well, I would say that P is inversely related to N, right? Because if there's only one student renting the whole apartment, you have to, that one student has to pay the entire monthly rent for the apartment. Two students gets divided by two. Three students it gets divided by three. At 10 students, it gets divided by 10. Now each student's only paying a tenth of the rent. If two students have to pay $700 each, how much money would they have to pay if there were five students instead of sharing the rent? Let's look at it. So they're paying $700 each, and there's two of them. Well, now that allows us to solve for what their rent actually is. The actual rent is $1,400 per month. Okay. Now that we know that, we can go back and say, what would the payment be for, what they say, five students? So let's take the $1,400. I guess those dollars has a unit. Okay. And we're going to divide that among five students. I think it's 280, isn't that? P equals $280. Of course, that'd be per month. That was all per month, per month. Yeah, like that. Yeah, there you go. All right. So to recap just that tail end of the part, right? This apartment costs $1,400, and we know that because if two students are sharing costs, they each have to pay $700. This is dollars also per month. Okay. Okay. Now that we know the apartment costs $1,400, say, hey, what if there were five students all sharing the rent? You divide that out, it's $280 per student. Okay. Let's do one more here. Communications. On average, the number of calls each day between two cities is directly proportional to the product of the populations and inversely proportional to the square of the distances between the cities. Now, they give you this setup here, and this is an interesting looking setup, definitely from a physics point of view, and I'll point out why. So see the number of calls, well, each day, so equals some constant times the population in one city times the population in another city divided by the distance between the cities squared. Okay. Now, if you stand back and look at this formula, especially if you've been through physics class, you say, well, this definitely looks like at least two familiar formulas. This could be universal gravitation. Like, what's the gravity force between the Earth and the Moon? I could put force here in the place of C, right, for a number of calls. Force. How much is the Earth pulling on the Moon, vice versa? And it's the universal gravity constant times the mass of Earth times the mass of the Moon divided by the distance between the Earth and the Moon squared. Right. Another application of the same structure formula is electrostatic force. So again, some kind of force here, say between an electron and another electron, right? Could be electrostatic constant times the charge in coulombs for each charged particle multiplied together, and then divided by the distance between them squared. Yeah, so this is definitely a physics looking type formula, right? And I think it makes sense in the context of this particular story too, right? The more populous each city is, the more likely there are to be phone calls from one city to the other because there's more people to call each other, right? And then the further apart they are, well, there would be fewer calls because maybe like how far do your family and friends move or something. I can see that being reasonable too, right? Like how often are you going to call someone in Gainesville a few hours away? How often are you going to call someone in Shanghai on the other side of the world? Probably not as often, I guess. Probably if I surveyed the entire class and got some numbers on that. Right. And then we have this whole table of values for calls between cities. Notice the city calling itself is marked out, so we're not going to consider that. But any city can call any other city, right? Or someone in the city. Question A, the average number of daily calls between Indianapolis and Birmingham, which shows up here and also here, whether it's I to B or B back to I, right? Indianapolis, Birmingham, is 479 million. Sorry, that's 479, or sorry, 16,000. That's what it is, right? So this table gives you the distance values in miles, right? We got 16,000 phone calls each day. Find the value of K, round to the nearest hundred. Let's do it. So I got 16,000 phone calls equals. Now we're going to solve for this K. This is actually the method I've been urging you guys to do this entire video, right? But now the book is finally saying, hey, let's actually get a K and solve for K. Okay. And then Population of Indianapolis is 872,680. Population of Birmingham is 210,710. The distance between those cities is 479 miles, but don't forget to also square that because we got this inverse square relationship, right, between the number of calls and the distance. Okay, so now I can get K, right, by taking my 16,000 calls, multiplying by 479 squared, and dividing by each of these numbers. But correctly this here, 872,680, and then 210, 710. Right, I'm getting K equals 0.01996. They said round to where? Oh, the nearest hundred? That's like right about here. Okay, now this would have weird units. What does this have? This is calls miles squared over people squared. Okay, so weird units. Okay, that's approximately, it's very, very, very close to 0.02, and then same set of weird units. Okay, great. Um, find the, okay, so we got that. Well, with these units, just keep those two. Right, so that's question A. Question B says, find the average number of daily calls between Tallahassee and each other city listed. Okay, we did it. All right, so number of calls. Let's go Tallahassee to Birmingham. We'll start with that. So 0.02. The population of Tallahassee is 191,000. Population of Birmingham is 210,000. And we'll divide by the distance between those two cities is 301 miles. And don't forget to, of course, square that distance. Right? So the number of calls between those two cities should be 102, 191,049, 210, 710 over 301 squared. Okay. About 8,886 calls. All right, so maybe getting close to 9,000 calls right there. Okay. All right, let's do the other two cities you connect to, and then we'll just wrap this up there. All right, so 62B continued. How about the calls from Tallahassee to Indianapolis, or vice versa, Indianapolis, Tallahassee, back and forth calls. So we got a K value of 0.02, population of Tallahassee, 191,049, population of Indianapolis, 872,680. All right, and then divide by the distance between Tallahassee and Indianapolis, 778 miles. Don't forget to square that. See what this is. 0.02, 191,049, 872,680 divided by 778 squared. I'm looking at 5,509 phone calls. Okay. And then finally, let's do number of calls from Tallahassee to San Francisco. San Fran. Okay. So 0.02. Okay. Population Tallahassee, 191,000. Okay. I'd say, ooh, San Francisco, that has the largest population here. Actually, it's not that bigger than Indianapolis now I'm looking at it. But whatever the metropolitan area is defined as, or maybe it's like city limits. But it is so far away. So it's on the other coast. So this is from Tallahassee to San Francisco. They got 2,600 and something miles. And that's being squared. Okay. So maybe this is even a lot fewer calls just because it's so far away. Let's see if that's true. 0.02 times 191,049, 884,363 divided by 2637 squared. Look at that. Yeah, just 486 calls. Because San Francisco is so far away. It's on the other coast. I mean, not calling too deep. All right. And that right there will
be a wrap on 9-5.